Hello everybody. Today we're going to do an example problem related to sorption. This is problem 9.1. If you're interested, here on Sakai, it's under practice problems and it's in a file called practice problem 9.1 and sorption isotherm. The sorption isotherm will be a separate video that I'll probably make right after this one. Alright, so the problem is you want to know what fraction of atrazine is in the truly dissolved phase. First in a lake with 2 milligrams per liter of particulate organic carbon. Second in a marsh with 100 milligrams per liter of total solids and a fraction of organic carbon of 0.2. And finally in an aquifer where the porosity is 0.2 by volume. The density of minerals is our standard number of 2.5 kilograms per liter. And FOC is 0.005, which is low but not unreasonable for an aquifer, probably quite. Most aquifers are relatively sandy, and therefore that's a reasonable value of FOC. So to do this, first thing we got to do is we got to figure out what is the KOC value for atrazine. We can use a value from a text. We could use a linear free energy relationship. There's a couple of ways we can do this. So if we look in the textbook, you might remember this figure, figure 9.9. This is in the lecture notes. This was for atrazine, and it was a histogram, a number of experimental values for log KOC that had been measured in a bunch of different papers in the literature, and it had kind of a bimodal distribution. So somewhere in here, somewhere around 2.1, somewhere between maybe 2.5 and 1.7 is a reasonable value for log KOC for atrazine. So we have a couple of options here. We could just pick a number out of a hat. The other thing that we could do is we could try to predict log KOC from one of these linear free energy relationships. So we have this table 9.2, which is a bunch of linear free energy relationships that relate KOC to KOW. And we can look up KOW for atrazine. In the book, they give a value of 2.65 for log KOW of atrazine. So if we wanted to predict using one of these linear free energy relationships, we could go down here. Is it an alkylated and chlorinated benzene or a PCB? No. Is it a PAH? No. Is it chlorinated phenol? No, it is not. What is atrazine, by the way? So we should probably show you the value for atrazine. I had it up here, but apparently I got rid of it. So let's go to our friend Wikipedia and look up atrazine. So here's atrazine. So it's got this cyclic structure, it's got the 2 amino groups, it's got a chlorine. Okay, so atrazine's kind of a funky looking chemical. So it turns out it is a phenylurea. So one of these equations, H, I, or J, might apply. This one's only alkylated and halogenated phenylureas, methylureas, and phenyl dimethylureas. And this one is only alkylated and halogenated phenylureas. I don't know which one to choose. I think it's really unfortunate that your book likes to use the term bipolar. I know people who actually are bipolar, and it's not a laughing matter. So unfortunate use of terminology there. But I can see how equation 926H would make sense. 926J might also make some sense. Sorry, HI and 926J might also make some sense. So we have our slope, which we're calling A, and our intercept, which we're calling B, right? So there's A, and there's B. So for the first equation, it's 0.49. And the intercept is 1.05. For the second equation, it's 0.59, and the intercept is 0.78. And for the third equation, it's 0.62 and 0.84. Okay, so those are our slopes and intercepts. So our calculated log KOC value would be A times log KOW plus B, and then if I can F4, at least on my keyboard, F4 will put the dollar signs on there. Now I can copy this down. Okay, so I end up with a value around 2.4-ish. So let's just, for the purposes of this this illustration, use 2.4. And so that means that our KOC is 10 to the value of 2.4, about 251. Too many decimal places. I hate it when you have too many decimal places. It drives me crazy. All right. So here's a reasonable value of KOC, about 250. So now, armed with that, we can do part A. What is the dissolved fraction of our chemical in a lake with 2 milligrams per liter of particulate organic carbon? So POC would be the ratio of solids to water already multiplied by FOC. Because it's the ratio of solids to water would be like total suspended solids, might be 10 milligrams per liter. FOC might have been 0.2, and that would give you the 2 milligrams per liter of particulate organic carbon. So our equation that we saw for the fraction of the chemical in water was this, but we're using KOC instead of KD, so we're actually going to use this form of the equation. KD is equal to KOC times FOC. So let's get rid of that for now. We're going to use this equation. All right, so FW is equal to 1 divided by parentheses, don't forget your parentheses, 1 plus the ratio of solids to water times FOC, which we know is 2 milligrams per liter, times KOC, which is 251. Oops, forgot to put my equal sign in there. Equals times 251. So my fraction of the chemical that's dissolved in water is less than 1%. Does that seem right to you? No, it's not right. Atrazine has a low log KOW value of 2.4. And so it's useful to log this away in the back of your head, that something with a log KOC of about 2.4 is not going to be sorbed. It's going to be dissolved in water. So what did we do wrong here? What we did wrong here is POC is 2 milligrams per liter, but KOC it has units of liters per kilogram. So to get this right, we need to multiply our 2 times 1 to the 10 to the minus 6. Oops. Times, there we go. 2 times 1 times 10 to the minus 6 times KOC. It actually turns out that our chemical is 99.95% dissolved. So that makes a big difference. And this is the morality story about why you always need to keep track of your units, right? So this 2 times 1 times 10 to the minus 6, that's how many kilograms per liter of POC we have. 0.0000000 whatever 2. All right, so that's part 1, or part A. Part B is in the marsh with 100 milligrams per liter solids, and FOC is 0.2. So our ratio of solids to water is 100 milligrams per liter. Our FOC is 0.2. These are all very reasonable values for a marsh. FOC is often around 0.2. So let's get this straight right from the beginning and not mess this up. 100 times 1 exponent minus 6, that's how many kilograms per liter of ratio of solids to water we have. So now our FW is 1 equals 1 divided by parentheses 1 plus ratio of solids to water times FOC times KOC. Booyah! Now it's 99.5%. So it's still mostly dissolved. Before it was 99.95%. Now we've gone from, the POC, just to be clear, POC here would be RSW times FOC. So it's now 20 milligrams per liter. So it went from 2 milligrams per liter to 20 milligrams per liter. And the fraction that was dissolved really didn't change much, from 99.95% to 99.5%. So this is a chemical that's really not that hydrophobic in the grand scheme of things. You can tell just by looking at the structure here, it's got a lot of polar functional groups. This is not a particularly hydrophobic chemical, and so in the water column, most of it's going to stay in the dissolve phase. So now let's do part C in the aquifer. So let's see. Whenever you don't know what to do, you play for time by typing out all of your knowns. So porosity is 0.2. Density, which is rho of the minerals, 2.4. kilograms per liter. FOC 0.005. Okay, so 1 liter of aquifer, if the porosity is 0.2, then that means that is 0.2 liters of water. So 1 liter of aquifer contains 0.2 liters of water and 0.8 liters of solids, right? 0.8 liters of solids, is 0.8 liters times 2.5 kilograms per liter is 2 kilograms of solids. So our ratio of solids to water is 2 kilograms divided by 0.2 liters. So that is now kilograms per liter. And that's already in kilograms per liter, and we don't have to worry about converting units. So now we just go back to our favorite equation, which we've sort of lost up here. So let's drag it back down. F sub W is equal to 1 divided by parentheses 1 plus ratio of solids to water times FOC times our KOC value. And now, lo and behold, only 7% of our chemical is now dissolved in water. We went from 99 point whatever percent being dissolved in the surface water and in the marsh, but in the aquifer only 7% is dissolved. So remember, we had something called a retardation factor, which was equal to 1 over the fraction in water. So here's our retardation factor. And what this factor means is that when the water moves 13.56 meters, the atrazine moves only 1 meter. So as it's flowing through the groundwater is moving a lot faster than the atrazine. Alrighty, see you on the other side.